2 years ago, I was putting the final touches on an elm dining table. It was one of those serious commissions, the kind that keeps you awake at night thinking about grain direction and moisture content. I'd spent 3 weeks of pure, focused labor in my workshop, from the painstaking glue-up of the slab to the final sanding stages. When you're running 180 grit paper over a surface that large, every pass feels like it takes an eternity. But you do it because the wood deserves that level of respect. I was at the very end of the process. The table was standing on its legs, and I was doing that one last sweep with my palm. The blind check, where your skin tells you what your eyes might miss. That's when my finger caught it. A tiny hairline crack, barely 5 millimeters long, right on the edge of the tabletop. It wasn't a structural failure or a deep split. It was a classic cosmetic defect, a little tension pocket that had stayed hidden in the fibers until the very last moment, right when the elm finally settled at its equilibrium of 8% humidity. The internal stress of the wood drying just enough had opened it up like a silent command. And I'll be honest with you, I got lazy. On the shelf behind me, I had rows of modern solutions, 3 types of wood filler: acrylic, epoxy, and some professional grade stuff that promised a perfect color match in bold letters on the tin. I picked the one that looked closest to the elm's natural tone. I pressed it in, leveled it with a spatula, waited for it to cure, and sanded it flush. Then I applied the oil. The filler didn't just show up, it screamed. It wasn't just a color mismatch, it was a dead, pale bandage sitting on a living, breathing piece of timber. It looked like a piece of cheap plastic stitched onto a high-end wool suit. While the oil soaked into the surrounding wood, darkening it and revealing that deep, chatoyant shimmer that elm is famous for, the filler stayed flat and lifeless. It never was wood, and no matter how much pigment the factory pumped into that tube, it was never going to behave like wood. It doesn't breathe. It doesn't change color with the light, and it doesn't live. It just sits there, a foreign object that catches the light at the wrong angle every single time you walk past it. 3 months after that failure, I found myself in a restoration workshop in Sergiev Posad, Russia. I was there to observe a master who was working on 15th century iconostasis carvings. He was dealing with a complex oak relief that had a visible chip in a prominent spot. I expected him to reach for a modern polymer or some high-tech 2-component resin. Instead, he reached into an old wooden drawer and pulled out a glass jar filled with what looked like amber-colored gelatin or translucent hard granules. He tossed a handful into a tin mug, added some water, and set it on the edge of a small heater. Within 20 minutes, a scent began to drift through the shop, a smell I hadn't encountered since I was a boy in my grandfather's workshop. It was the smell of real craft. In that mug, he was cooking hide glue, specifically hide glue, the same animal-based protein adhesive that furniture makers used to build masterpieces for centuries before PVA glue ever existed. The master took a pinch of the finest oak dust from the very same piece he was working on, mixed it with the hot glue until it formed a thick paste, and pressed it into the chip with a damp finger. The next day I couldn't find the repair, not because it was cleverly hidden, but because for all intents and purposes, the defect had ceased to exist. The repaired area had absorbed the oil finish exactly like the rest of the board. It had become part of the wood. To understand why this old-fashioned method works where modern chemistry fails, we have to stop lying to ourselves about what we're putting into our furniture. Most store-bought fillers, whether they're acrylic or latex, are essentially a mix of polymer binders and mineral fillers like chalk or talc. When you rub that into a crack, you're shoving a piece of inert plastic into a biological organism. Physics doesn't care what the label on the bottle says. You can't cheat the laws of materials. The first issue is the coefficient of thermal and moisture expansion. Wood is anisotropic. It moves constantly. If the humidity in your house shifts by just 2 or 3%, the wood expands or contracts, and it does so differently across the grain than along it. But your acrylic or epoxy plug, it's isotropic. It expands the same way in every direction. Within a few seasons, microstresses develop at the boundary between the plastic and the wood. After 5 years, you'll see a hairline ring around the repair. I've seen it on my own pieces from 20 years ago. What looked perfect the day I delivered it eventually looked like a loose tooth or a failing dental filling. The second issue is porosity. Wood is a network of capillaries. Oil, wax, or stain travels deep into those pores. A synthetic filler is a brick wall. It absorbs nothing. Even if you match the color perfectly in its dry state, as soon as you finish the piece, the wood will darken and deepen while the filler stays exactly as it was. At any angle, the light reflection will be different. The matte, deep glow of wood versus the dull, light-scattering surface of plastic. Finally, there's mechanical density. Fillers are almost always either softer or harder than the surrounding wood. On a tabletop that gets wiped down every day for a decade, you'll eventually get either a small pit or a slight bump because the materials wear at different rates. The old masters didn't need a lab to tell them this. They felt it in their fingertips. If you want to fix wood, you use wood and a binder that is chemically compatible with natural fibers. Today, I'm going to show you exactly how to prepare this composite, how to maintain that critical 60°C, 140 FN temperature, and how to harvest the right grade of wood dust to make your repairs truly permanent. We're going to look at the mistakes that cost me months of trial and error, and I'll share that final secret from Sergiev Posad that makes a repair disappear even under a magnifying glass. The tradition of using animal glue in tandem with wood dust isn't just a grandfather's trick born out of scarcity or a lack of modern options. It is the result of a brutal, centuries-long process of natural selection for technologies that played out across Europe and Russia from at least the 15th century. To truly grasp why this works, you have to step away from our modern world of air-conditioned workshops and digital moisture meters. Think about the environment of a master shop in that era. There was no climate control. Furniture was often built in unheated spaces or rooms that were only periodically warmed by a hearth. A cabinet might be finished in a damp spring and then moved into a stone castle or a drafty cottage where the relative humidity could swing from 30% in a dry, frozen winter to 90% in a rainy autumn. The masters of that time knew that if their work failed, their reputation and their livelihood died with it. In the German woodworking guilds, the Zunfte, there was a terrifyingly strict regulation for any apprentice wishing to earn the title of master. It was called the Stückprüfung, or the masterpiece exam. The elders of the guild would inspect the candidate's work, often a large, flat-surfaced dining table or a complex paneled chest, using only the raking light of a single candle held at a low angle against the surface. If that flickering side light revealed even the slightest shadow of a patch, or if a repair reflected light with a different texture or luster than the surrounding timber, the exam was a failure. The apprentice was sent back to work as a journeyman for another 3 years. There was no close enough in a world where furniture was expected to outlast the grandchildren of the person who commissioned it. In the Russian tradition, particularly in Sergiev Posad, which has been a global center for wood carving and high-level restoration for hundreds of years, the approach was even more disciplined. They worked with oak, linden, and birch, using what they called faithful glue, or vernis-clés. They didn't use that term out of some poetic nostalgia. They called it faithful because the glue was chemically faithful to the material it held together. This was hide glue, rendered from the collagen-rich connective tissues of the leather-making process. The central philosophy was built on a single engineering principle: material homogeneity. To understand the engineering behind this, we have to look at the wood as a living tissue, of cellulose and lignin. Animal glue is essentially a protein, collagen. On a molecular level, this protein has a structure that allows it to form incredibly strong hydrogen bonds with the wood fibers. When you mix that hot, liquid collagen with the dust of the very same board you are repairing, you aren't just filling a hole with a foreign filler, you are creating a biological composite. This composite shares the same density, the same thermal conductivity, and most importantly, the same hygroscopic behavior as the wood around it. It expands when it gets damp and shrinks when it dries, moving in perfect lockstep with the rest of the table. So why did we lose this? The answer is as simple as it is cynical. Time and the industrialization of craft. The Industrial Revolution and the chemical boom of the mid-20th century brought us PVA, epoxies, and acrylics. They are convenient. You can pop a cap, squeeze a tube, and walk away. For a factory that needs to move a sofa from raw timber to a shipping container in 12 hours, these chemicals are a miracle. But we traded longevity for that convenience. Modern fillers are designed to help a contractor close out a job today and get paid. The traditional mix of dust and hide glue was designed so the object would still be standing, unbroken, in the year 2300. Many of my colleagues ask me why I bother with a glue pot, a thermometer, and a heater when I can buy a tube of matching filler for $10. My answer is always the same. I've gone back to look at some of my own work from the early 2000s, pieces where I use those high-tech acrylic fillers to save myself 20 minutes of prep. Today, those repairs look like white plastic scars. The chemistry has aged and shrunk at a different rate than the wood. But where I use the dust and the hot glue, the surface is still one single, unbroken thought. Using this method is an act of respect, not just for the wood, but for the time you're putting into your work. You aren't just fixing a defect, you're restoring the wood's integrity using the same laws of physics that grew the tree in the forest. This transition from patching to reconstructing is the mental shift every master has to make. And it starts with understanding that the best material for fixing wood is quite literally wood. Now let's move to the workbench. If you want this to work, you have to leave your haste at the door. In this craft, nothing good is ever born from a rush, and that goes double when you're working with animal-based adhesives. We're going to break the whole process down into 6 distinct stages, from the chemistry of the binder to the final stroke of the sandpaper. Technique 1. Preparing the adhesive. In traditional cabinetry, we use hide glue, Mizdrovi Kli. It's often confused with bone glue, but there's a massive difference in the physics of the two. Bone glue is brittle. It's perfect for the sounding boards of musical instruments where you want high rigidity. But hide glue, rendered from the dermis layer of skins, possesses a colossal elasticity and grab. For filling cracks, it is the only choice because it breathes and flexes in perfect harmony with the timber. The process starts 12 hours before you even touch a chisel. I take the dry granules, they look like coarse amber sand, and submerge them in clean water at a weight ratio of exactly 1:2. That's 50 grams of glue to 100 grams of water. By morning, the glue has bloomed into a dense, firm jelly. My biggest mistake in my early years was trying to heat this over a direct flame. I burnt the batch in seconds, and the smell was so foul I had to clear out of the shop for the day. You must use a water bath, a double boiler. I use an old electric glue pot, but any pot of water with a glass jar inside will work. Your target temperature is strictly between 55 degrees Celsius and 65 degrees Celsius, 131 Fahrenheit to 149 Fahrenheit. If you don't have a digital thermometer, watch the water. It should be steaming but never bubbling. If you push that glue past 70 C, 158 F right, the long-chain protein molecules begin to snap. The glue will look fine, and it will still be sticky, but its structural strength will drop by 2/3. When it's right, the glue should run off your stir stick in a smooth, translucent stream, exactly like warm honey. If it's stringy, add a teaspoon of hot water. If it's watery, let some moisture evaporate off. Technique 2. Harvesting the native filler. This is the most common point of failure. Most guys just empty the bag from their random orbital sander. Don't do that. That bag is a graveyard of old finishes, different wood species, and microscopic particles of aluminum oxide from your sandpaper. If you use that, your patch will turn into a muddy, gray smear the moment you apply oil. For a serious repair, I harvest the dust manually. I take offcuts from the actual project, the same board if possible, clamp them in the vise, and sand them with fresh 180 or 220 grit paper. Why this specific range? I've run the tests. Dust from 80 grit is too coarse. It looks like beach sand in the crack. Dust from 400 grit is a flour that turns into a featureless sludge when mixed with glue. But 180 grit gives you microfibers, tiny elongated particles that actually mimic the grain structure. I sweep this dust onto a clean sheet of white paper with a soft brush. It must be bone dry and identical in color to the workpiece. Technique 3. Creating the composite paste. On a clean piece of glass or acrylic, I form a small mound of the dust with a well in the center. I add the hot glue literally drop by drop. You are looking for the consistency of soft modeling clay or plasticine. The paste should hold its shape if you roll it into a ball, but it should still yield easily to finger pressure. You have a window of about 3 to 5 minutes while the glue is hot. Animal glue begins to gel the moment it drops below 40 cc's, 104 Fahrenheit. Once it gels, its ability to wet the wood fibers, the adhesion, plummets. If your mix gets cold and stiff, do not try to revive it with more water. It will lose its stability. Toss it and mix a fresh batch. It only takes a minute, and the integrity of the table is worth that minute. Technique 4. The mechanical lock and application. Before I ever put the paste in, I prepare the lock. I take a marking knife or a narrow chisel and slightly widen the crack at its base, creating an undercut or a reverse angle. This is a swallowtail or dovetail joint on a microscopic scale. Even if the wood undergoes extreme seasonal movement, that plug is physically trapped inside the mass of the wood. It has nowhere to go. I don't apply the paste with a metal spatula. I use a damp finger. This is a secret the old-timers in Russia taught me. Your finger provides two things a spatula can't: targeted pressure and body heat. The heat from your skin keeps the glue liquid for a few extra seconds, allowing it to wick into the micropores of the crack. The moisture on your skin prevents the glue from sticking to you instead of the wood. You need to overfill the crack. Because this is a water-based system, it will shrink as it dries. With hide glue and dust, you can expect 10% to 15% shrinkage, so leave a distinct hump or mound over the repair. Technique 5. Deep defect reinforcement. If you have a knot hole or a gouge deeper than 5 millimeters or wider than 3 millimeters, a pure paste will shrink too much and might even crack itself. In these cases, I use internal armoring. I don't use dust for the base layer. I use fine shavings, the little curls from a hand plane or a cabinet scraper. I soak these curls in the hot glue and pack them tightly into the bottom of the hole. These shavings act like rebar in concrete, holding the volume and preventing the mass from collapsing. I let this structural layer dry for 6 hours. Then I come back and apply the fine-grained dust paste as the final cosmetic cap. Technique 6. The natural cure. Do not use a heat gun. I've watched beginners try to dry a patch in 10 minutes with a blow dryer, and it's a disaster every time. The heat forces the moisture out too fast, causing the glue to case harden and snap away from the walls of the wood. In my shop, at a steady 20 Celsius, 68 F, I leave it for a full 12 hours. When it's dry, that mound will have settled, and it will be as hard as a piece of horn. When you sand it back, start with 150 grit on a hard sanding block. This is the moment of truth. When you sand a standard acrylic filler, your hand feels the transition. It goes from the hard resistance of the wood to the soft mush of the plastic. But here the resistance is uniform. The dust flying off the sandpaper smells and looks exactly like the rest of the board. I once did a test on a pine beam, 2 holes, one with store-bought acrylic and one with this method. After a year of being moved from a damp basement to a hot, sun-drenched deck, I hit the beam with the back of an axe. The acrylic plug literally popped out and hit the floor. The hide glue repair stayed put. On a chemical level, the collagen and the cellulose had become one structure. You aren't just filling a hole, you are recreating the material itself. When the tools are finally wiped down and resting in their racks, and the fine dust in the shop has settled into that quiet, evening stillness, it's time to talk about something more important than the glue pot or the chisel. We need to talk about how we look at our work. Over 20 years of making mistakes, I've realized that our hands are often held back by how our brains are wired. I've identified 4 specific patterns of thinking, mental habits that most of us fall into, that actually keep us from understanding the wood. I spent a decade trapped in these same loops before I learned to see past them. The first pattern is a blind, almost religious faith in the label. We've been conditioned by big box stores to believe in names like Early American, Golden Oak, or Dark Walnut. But in the real world, oak isn't a color, it's a biological spectrum. The chemical makeup of a white oak harvested from a north-facing limestone ridge in Kentucky is fundamentally different from a red oak grown in the sandy soil of the coastal plains. Their tannin levels vary wildly, and those tannins determine how the wood reacts to oxygen and finish. When you buy a jar of pre-mixed filler, you're buying a dead, mineral-based average, a marketing compromise designed to satisfy everyone and fit no one. For years, I wasted hours trying to tint store-bought goop with universal pigments, struggling to hit a moving target. I finally realized that the only perfect match for a board is the board itself. The color you're looking for isn't on a shelf in a plastic tub. It's under your workbench in the form of dust. Stop looking for a match in the store. Start looking at the material in your hand. The second pattern is treating our waste as if it's garbage. We've become a buy, use, discard culture, and that's infected the workshop. Every time you empty your dust collector into the trash, you are throwing away the most valuable repair kit you will ever own. On the shelf above my main bench, I have about 40 small glass jars, all meticulously labeled. Black walnut, 8% moisture. Spalted maple, air-dried. Old-growth heart pine, English elm. I call it my woodworker's pharmacy. It takes exactly 30 seconds at the end of a project to sweep up a handful of clean 180 grit dust and put it in a jar. Over time, this collection becomes an asset that saves you hours of frustration. It turns your process from a linear one into a cyclic one, where the leftovers of today's masterpiece become the invisible repairs of tomorrow's legacy. The third pattern is the modern obsession with convenience over longevity. Our industry sells us time, not quality. We reach for the acrylic filler because it cures in 10 minutes and we can sand it immediately. But if you're building a piece intended to live for 50 or 100 years, that 10-minute convenience is a trap. I often think about a mistake I made early on. I wasn't confident in a joint I'd cut, so I drove a second and then a third screw into the assembly, thinking more steel meant more strength. All I actually did was create a rigid, unyielding point of tension that eventually caused the wood to split as it tried to move with the seasons. I had redistributed the failure instead of solving it. The same logic applies to fillers. A 5-minute chemical fix creates a long-term engineering conflict. The hide glue and dust method takes an extra hour of prep, but it creates a bond that respects the timeline of the wood. The fourth pattern is the fear of the defect. We've been taught to see a crack or a knot as a disaster to be hidden or masked. The old masters saw these things as a dialogue. They understood that wood is a living, moving entity, and a crack is just the material telling you where the tension is. When you use the dust and glue composite, you aren't hiding a flaw under a layer of plastic. You're restoring the structural and visual integrity of the fiber. You stop being a person who patches holes and start being a person who understands the material's life cycle. Once you've seen a 20-year-old repair stay invisible through 4 different house moves and a dozen seasons, you stop fearing the wood's natural movement. You start to trust the physics. You don't have to change your entire philosophy overnight. Just try it on one small project, one tiny check in a tabletop. Put away the tube of chemicals and light the glue pot. Feel the warmth of the collagen, smell that ancient scent of the shop, and work the paste with your fingers. In that moment, you're connecting to a chain of masters that stretches back hundreds of years. And that brings me to the secret I promised you at the start. Andrei Viktorovich, the master restorer from Sergeyev Posad, watched me finish a patch one afternoon. I had matched the color perfectly, the shrinkage was 0, and the surface was flush. I was proud of it. He looked at it, then reached for a small brush with stiff, brass bristles. It was a specific gauge of wire, about 0.15 millimeters to 0.2 millimeters. Before I could stop him, he took that brush and made 3 or 4 sharp, aggressive strokes along the grain, right over my perfect patch. I nearly had a heart attack, but then I looked closer. He wasn't scratching the wood, he was opening it. Because the glue and dust paste is a composite, it can sometimes sand down a bit too smoothly, becoming a blind spot that reflects light more uniformly than the porous wood around it. Those brass bristles, which are softer than steel and won't bite into the wood, were knocking out microscopic bits of the cured glue, creating tiny, artificial pores. When we applied the final oil finish, the oil settled into those micro grooves. The light stopped breaking at the repair site. The patch didn't just match the color, it matched the light-scattering properties of the oak. It became matte exactly where the oak was matte. It's a 10-second step that takes a repair from good enough to undiscoverable. It's the difference between a mechanic and an artist. At the end of the day, real craft isn't about having the most expensive tools or the latest chemical breakthroughs. It's about a quiet, honest dialogue with the material. It's about recognizing that nature already figured out the best solutions millions of years ago, and our job is just to listen. If you decide to fire up a glue pot for your next project instead of reaching for a plastic tube, then this conversation was worth every second. Take care of your tools, respect the wood, and above all, keep your hands busy. I'll see you in the shop.